Training a machine learning model requires the dynamic, Python-based environments of PyTorch or TensorFlow. But deploying that model requires it to run on a diverse, fragmented array of physical silicon. This gap creates the primary bottleneck in AI infrastructure. Integrating N frameworks with M hardware targets creates an unsustainable matrix of custom software bridges. This fragmentation traps models in vertical silos. When deployment engineers move code between stacks or specialized runtimes, the custom integrations often break. Solving this N-to-M dilemma requires a hardware abstraction layer to decouple the training code from the execution engine. This is why ONNX was created. It functions as a universal intermediate representation, a standardized language that sits between model authoring and hardware execution. Frameworks export to ONNX, and hardware vendors build execution providers that consume the graphs. This shifts the engineering complexity to a simple hub-and-spoke model. This decoupling reduces the engineering burden from an exponential N times M matrix of custom bridges to a linear N plus M scale. Because the torch.onnx.export command is a single line of code, developers often assume it functions like a lossless save-as operation. Relying on that assumption leads to models that pass all tests in training but behave unpredictably in production. This dashboard tracks a YOLO v8 object detection model. It achieved 99% accuracy in native PyTorch, yet dropped to 46% immediately after its conversion to ONNX. This accuracy collapse follows a misconception about the exported file's internal structure. ONNX is a rigid, strictly typed, static mathematical contract. It does not carry over the dynamic flexibility of the original framework. To find the source of these silent production failures, we have to reverse engineer how ONNX serializes and executes mathematics. Treating an intermediate mathematical representation as a direct code replica creates catastrophic blind spots in the deployment pipeline. Looking closely inside a raw.onnx file actually reveals serialized static mathematics rather than standard dynamic executable code. The architecture uses protocol buffers to define a directed acyclic graph. A model proto container holds the graph proto. Inside, each node proto is an individual call to a mathematical operator with its learned weights locked in. This environment is strictly typed. It demands absolute precision between connecting edges and forbids implicit typecasting. To maintain consistency across different frameworks, ONNX uses Opsets, or operator sets. An opset is a versioned semantic contract. Declaring an opset version ensures the runtime evaluates a node exactly as defined at the time of export, isolating the model from future framework updates. This structural rigidity guarantees that models remain portable over time, though it requires discarding the dynamic control flow available in Python. The ONNX file is a static blueprint. It requires a separate execution engine, the ONNX Runtime, to actually run. Before execution, the runtime performs shape inference, propagating tensor dimensions across the entire graph. This step happens at compile time, locking in precise memory boundaries before the first calculation begins. To interface with physical silicon, the runtime uses modular plugins called execution providers. The runtime evaluates the operators in the graph against these providers, such as NVIDIA's TensorRT or Intel's OpenVINO. It then partitions the graph, dispatching dense subgraphs to the GPU while kicking unsupported mathematical nodes back to the CPU. This modular dispatch system abstracts away the system's engineering, allowing one model to achieve high hardware utilization across entirely different environments. The primary friction occurs when a dynamic Python script is forced into this rigid, static pipeline. During export, ONNX traces execution using a dummy input. It records only the specific logic path triggered by that one tensor. Dynamic loops and if-else logic are unrolled and permanently crushed into a single, unbending computational line. If production data requires a different logical branch than the dummy input, the static graph fails. Optimized engines like TensorRT also impose strict boundaries on dynamic shapes to prevent runtime memory allocation failures. Highly variable internal shapes often trigger a fallback to the CPU execution provider, leading to sudden latency spikes in production. Edge deployment introduces a further failure mode, aggressive quantization. High-precision FP32 weights are downcast into low-precision INT4 formats to fit on mobile devices. This extreme downcasting can cause mathematical underflow during matrix calculations. This creates semantic drift. The decision boundary curve shifts subtly, causing accurate data points to fall into the wrong classification zone. Semantic drift silently degrades accuracy without throwing runtime errors, making rigorous validation sets a requirement for any deployment pipeline. Today, massive autoregressive generative AI models, like the Gemma-4 family, are testing the structural limits of the ONNX standard with highly irregular architectures. These designs rely on per-layer embeddings and asymmetric key-value caching, where memory needs change with every token generated. These dynamic requirements cannot be mapped into static ONNX nodes without causing shape inference errors. To run LLMs on the edge, the ecosystem uses external orchestration layers like ONNX Runtime GenAI. This layer sits outside the static directed acyclic graph, managing the autoregressive loop manually. It manages the KV cache state dynamically across iterations, preserving memory externally instead of passing it through the static graph. Moving state management to an external orchestrator allows massive models to execute on constrained consumer hardware. Browser-based deployment via the WebNN API relies on this external bypass to run quantized models with zero server latency. Treating ONNX as a rigid mathematical contract allows engineers to anticipate semantic drift, leverage orchestration layers, and successfully deploy AI to the edge.